Hey, Brianna.
Hi,
How are you today?
I'm good. How are you?
Good. So, what do we got going on in calculus today?
So we're getting started on the first derivative test.
Okay.
Have a couple problems with key sign.
Okay.
Okay, so on page 182, or actually 186.
Do we have the same book?
Yeah, I think so.
180 what?
186.
Okay.
So the first one he signed was problem 24.
F of x equals x plus 2 quantity squared times x minus 1?
Yes.
Okay. Now let me write that down here. X plus 2 quantity squared times x minus 1. And find the critical numbers of f, if any. Find the intervals where it's increasing, decreasing. Apply the first derivative test to identify all extrema. Okay. So, what's the first derivative?
X squared plus 4. Oh.
Now, hold on. What we want to apply here is the product rule.
Okay. So,
Okay.
2
So pick one or the other. I don't really, you can use either one. In other words, the product rule is u prime v plus v prime u. But you can do these in either order.
Mm-hmm.
The problem I have with most students is I don't know which order they're going in. So what I usually tell them is do them in the same order. In other words, either take the derivative of that every time or take the derivative of that every time as your first step.
Okay. So
You do it.
I'll do the derivative.
You want. Okay.
Okay, so 2 times x plus 2
to the 1.
Mm-hmm.
And we do have to apply the chain rule here. In other words, we're multiplying it by the derivative of the inside, which happens to be 1. Plus what? Oh, oops, hold on. Times what?
Times x minus 1
Plus what?
plus x plus 2 quantity squared times 1.
Okay. Now if we simplify that, we have 2 times x plus 2 times x minus 1 plus x plus 2 quantity squared. So that's our first derivative. And let's see, what do they want? They want what did they want?
The critical numbers.
Okay, let's start with those.
Okay.
Critical points are equal to what?
Would it be 2?
Well, it's where the first derivative is equal to 0 or where the first derivative is undefined.
Okay, so -2 and 1 and 0.
2 certainly is a point. 1, I don't think the first derivative is 0 at 1. -2, that term is 0 and that term is 0. So -2 is definitely a critical point. But notice that 1 only makes that term 0. You need either the f prime to be 0 or undefined. In other words, if I ended up with a 1 over x, that's undefined at x equals 0.
Okay.
Well, I don't have that here, but at this point, the only point that I can see where the function is undefined is -2.
Yeah.
It's the only critical point. What's the next thing they want?
Find open intervals where the function is increasing or decreasing.
Okay. Where is it increasing? When the first derivative is what?
Greater than 0?
Yeah. Whenever the first derivative is greater than 0, the original function is increasing. Whenever the first derivative is less than 0, the original function is decreasing. So we have to solve this. First thing I'm going to do is multiply those two together, because I've got a lot to simplify here. Okay, so that's x squared plus x minus 2 all times 2 plus x plus 2 squared. Well, we can see that we need to multiply this out because I got a lot of simplifying. All of that has to be greater than 0. Now, how many x squareds do we have? We have 3. How many x's do we have?
6.
How many numbers do we have?
0.
Okay. So that's got to be greater than 0. Now, these aren't that easy to solve. What's my next step? Factoring. In fact, you can almost take any math problem that if you have a function that can be factored, that's almost always the next step. So if you don't know what to do and you're looking at a function that can be factored, try that.
Okay.
So what's the greatest common factor here?
3x.
It's left over?
X plus 3.
2.
2.
Okay. Now, the way you solve the product of two variables being greater than or less than 0 is with a line chart. And the first thing you need are the critical points of this function. What are they?
-2.
And 0.
Oh, right.
In other words, it's whatever makes that 0 or that 0. Okay, so I'm going to put those on my line chart. And now my goal is to determine whether this function, where it's greater than 0 and where it's less than 0. The first thing you do is try a point to the left of -2. Pick a point to the left of -2.
-3.
Okay. What's this 3x term when you pick minus 3? Is it negative or positive?
Positive.
No, if I plug in minus 3 for x, I get a negative right there.
Oh.
Okay? And I don't really care what the number is. I only care what the sign is. So
Okay.
any negative number that I plug in is going to make that negative. Now, when I plug in minus 3, what is that equal to? Negative or positive?
Negative.
Okay. So now I have a negative times a negative. That becomes a positive, which is greater than 0. So what I'm able to do on my line chart is say that all numbers to the left of minus 2 produce a positive first derivative, which means the original function is increasing in that interval.
Mm.
Now pick a number between minus 2 and 0.
Minus 1.
What is 3x when you pick minus 1? Is it positive or negative? Notice that we don't really care what this number is. The only thing we really care about is its plus or minus sign.
So it's negative?
What's this one? It's the second term.
That's positive.
Okay. Negative times a positive is negative.
Mm-hmm.
And what that tells us is that anything between minus 2 and 0 is negative. Now pick a number to the right of 0.
1.
Okay? What's this term when I pick 1?
Positive?
What's this term when I pick 1?
Also positive.
So that's positive. So now I know exactly where the original function is increasing and where it's decreasing. Where is the original function increasing? On what interval?
Below negative 2.
Do you use interval notation?
So it would be negative infinity to negative 2.
With parentheses, not bracket. Where else?
0 to infinity.
Okay. How about decreasing?
Negative 2 to 0.
All right. What else did they want to know? First derivative test. I remember you saying something about that.
Yeah.
Okay. So, if we look at the original function, we can tell it's a cubic, right? In other words, this is going to produce an x squared, this has got an x, so we're going to index with x cubed. So the original function, no doubt, has a couple of humps in it, like that. I mean, I might not have drawn it correctly, but this is typical of a cubic function, and you should know that.
Yeah.
Okay? And what our previous answer told us was that it was increasing up to negative 2. So let's redraw it. Up to negative 2, it was increasing. Between negative 2 and 0, it was decreasing. And then it was increasing again from negative 2 up. So that function could easily look like that. That would fit our increasing and decreasing intervals.
Mm-hmm.
Now, let's talk about the first derivative test. What the first derivative test, first of all, the most important thing you want to identify on any function is its local extrema. That's a local extrema, that's a local extrema. Because it is a cubic, it has at most two local extremas. Your local extremas are always at most one less than the degree polynomial. So when you're looking at a quadratic, you're only going to have one local extrema. It'll either be a minimum or a maximum. But when you're looking at a cubic, you have two. Well, the thing that I know is that at both of these local extrema, my first derivative is 0. Remember what the first derivative is. It's the slope of the tangent line. Well, both of those tangent lines have a slope of 0. So if I take the first derivative and set it equal to 0, I realize that the zeros come at 0 and minus 2. This is where the slope of the tangent line is 0. Notice that my increasing and decreasing did not include either of those 2 points. That's because that at those 2 points, the slope of the tangent line was 0.
Wow.
Now, the thing that's you want to know isn't just that the tangent line is 0. You want to know, is it a maximum or is it a minimum? Well, if I go back and I look at these 2 points, the thing that I notice, the first derivative test, is derivative of that's positive, correct?
Yeah.
And then it's 0, and then it's negative. Then it's 0, and then it's positive. So the first derivative test says that if you're going from positive to 0 to negative, that is a local maximum. And if you're going from negative to 0 to positive, that is a local minimum. That's what the first derivative test says. In other words, if you're to the left of the 0 and your slopes are positive, remember your slopes are the first derivative, and it comes out of the 0 negative, then you're looking at a local maximum. If it's the reverse, you're looking at a local minimum. Now, there's also something called the second derivative test. Have you had that?
No.
Well, let me introduce you to it because it is actually a little easier. So this is the first derivative, correct?
Right.
What's the second derivative?
4x.
Hold on, multiply that times that.
Oh, sorry. No, 6x plus 6.
Okay. Now, there is a second derivative. And think of the second derivative as merely the first derivative of the first derivative. That's all it is. It's not anything unique. It's just the first derivative of the first derivative. However, there is also something called a second derivative test for whether you're looking at a maximum or a minimum. And the second derivative test is if the second derivative is positive, then it's concave up matching positive. If the second derivative is negative, then it is concave down. And notice concave down has to be a maximum. So this goes with minimum, this goes with maximum. And these will give you the same results as the first derivative test. The difference is that the second derivative test is actually a little easier. In other words, if I wanted to know this first critical point, minus 2, whether that's a maximum or a minimum, plug it into the second derivative. What do you get?
Um,
You get a negative or a positive number?
a positive.
No. Plug in x equal minus 2.
Oh. So it will definitely be negative.
It's negative, which means the second derivative is negative, which means it's concave down, as we can see from our chart. That's concave down. You know about concavity?
Yeah.
Okay. Concave down always means a local maximum. Concave up always means a local minimum. So I don't need the first derivative test here. If I plug in the second critical point of the first derivative, which is 0, what is the second derivative when I plug in the second critical point?
Positive.
Positive means concave up. As you can see from the graph, that is concave up, and concave up means the local minimum. So there are two tests to determine whether you're, in other words, the first thing you do is take the first derivative and set it equal to 0. And all that does is locates all horizontal tangent lines. If you want to identify a local minimum or maximum, you have to go further. You either have to take the second derivative and figure out whether it's positive or negative at these points, or you have to apply the first derivative test. Either one of them usually answers the problem. Here, let me give you a different function just to explain this a little better. This function is y equal x cubed. Notice that it does not have a local minimum or maximum.
Yeah.
What's its derivative?
3x squared.
What are the critical points?
0.
Yep, that's it. Okay. Now, notice that, wow, this is neither a maximum or a minimum.
Yeah.
Well, what's the second derivative? Let's apply the second derivative test, which I prefer. Which gives you 6x. What is the second derivative when x equals 0? Is it positive or negative?
It's 0.
It's 0. It's neither positive nor negative. And what that means is the second derivative test is inconclusive. It does not tell you whether you're looking at a maximum or a minimum. So this is when you go back to the first derivative test. And this is really the only time I use the first derivative test. Remember what the first derivative test is. What are the slopes prior to the critical point? Are they positive or negative?
Positive.
What are they after the critical point?
Also positive.
Since they do not change sign, we do not have a maximum or a minimum there. Because all we have is a horizontal tangent line. But it's extremely important that it's neither a maximum or minimum. One of the beauties of calculus is it allows us to identify maximums and minimums of functions. A lot of times there are a lot of functions where you would really love to know, are there any minimums or maximums within that function? Well, the first thing you do is take the first derivative and set it equal to 0. And that defines either peaks and valleys like that, or it defines points like this, where you still have a 0 slope tangent line, but it's neither a maximum or a minimum. And you can figure that out by doing two things. First of all, the critical point, or rather the second derivative's critical point is 0. That's kind of a clue that it might not be a maximum or a minimum. And then when I do the first derivative test, I see that it's plus prior to the critical point, and it is plus after the critical point. If the sign does not change, then it is neither a maximum or a minimum, even if it went like that. You still have a 0 slope tangent line, but my slopes go minus, 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 0, minus, 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 minus. So to be looking at a local minimum or maximum, you have to have the slopes change direction either side of the critical point. Now, did we answer that whole question or not?
Yeah, I think so.
I can't remember what the entire question was, but it had to do with first derivative test. And since you have not had the second derivative test, then the only test you have to work with is the first derivative test. And the first derivative test asks you what are the slopes before and after the point where the slope is 0. And for it to be a local minimum or maximum, those slopes have to change sign. They have to either go from plus to minus or minus to plus.
Right.
All right. What else you got?
Question 30.
Okay. Let me look. So this is f of x equals x minus 1 to the 1/3. Same problem as you got?
Yes.
And find the critical numbers, find the intervals where it's increasing, decreasing, and apply the first derivative test to identify all relative extrema and use a graphing utility to confirm the results. All right. Anytime you have a calculus question and you don't know where to start, what's the first thing to do?
Pick the first derivative.
Yes, always. 98% of the problems that you're going to give me, that's always the first step. What's the first derivative of this?
1/3 times x minus 1 to the negative 2/3.
Okay. Let's put that with a positive denominator.
So, x minus 1, or 1 over 14.
Yeah, that's all the negative exponent means, is that I'm going to take the reciprocal of it. Now,
Okay.
let's talk about critical points. Are there any places where f prime of x is equal to 0?
Yes.
No. And the reason is that's f prime of x. For that to be equal to 0, its numerator has to be 0. Well, its numerator is 1. So there is no value of x that makes the whole fraction equal to 0. So there's no slope of the tangent line that's equal to 0. However, there is another point that is a critical point. What is that?
X equals 1?
Yeah, because that means you're dividing by 0. And dividing by 0 is a no-no. Wherever you're dividing by 0, that can't happen. So if the first derivative is not defined at x equal 1, then that's a critical point. Now, the next place is define where it's increasing or decreasing. So where is that greater than 0? And how do I figure it out?
So you can
Draw a line chart. The line chart is almost magical here. Okay? In other words, it will always answer these inequalities for you. And these are all relatively tough inequalities, and the only point you need to put on here is the critical point. You don't need to put the point 0 on there. It is not a critical point. To the left of this point, is my function positive or negative?
positive.
Why would they give you this problem? This is a toughie. There's a lot of things going on here mathematically that are way beyond the scope of calculus. And one of them is taking a negative number to, let's just talk about this, otherwise you're going to think I'm nuts. What is that equal to? Hold on, I'm looking for my, what the heck? I'm looking Wolfram Alpha. I don't seem to have it saved on my computer. Well, let me save it. And I'm going to take this number, minus 8 raised to the 2/3 power. Well, let's make sure that I input it correctly. Hold on. Okay, I did. I got minus 8 to the 2/3 power. What did you think the answer was before we did this on Wolfram Alpha? You take the root first. What's the cube root of minus 8? What is the cube root of minus 8?
Oh, negative 2.
Okay, and what's negative 2 squared?
4.
Seems relatively straightforward, right?
Yeah.
Well, look what they say. The answer is. It's minus 2 plus 3.4i. You see a
Weird.
4? You see a 4 in there? I don't.
No.
And they do put -1 to the 2/3 as part of their result, but their decimal approximation is an imaginary number. And I did some research on this. And it turns out that you're not really supposed to take fractional exponents of negative numbers if the numerator is not 1 and the denominator is odd. So this really does not equal -4. You saw the answer on Wolfram Alpha.
Yeah.
Okay? So like I said, I did a little research on this, and it's really advanced mathematics, but the bottom line was you don't take fractional exponents of negative numbers. I mean, you can take -8 to the 1/3. That's -2, clearly.
Yeah.
But if that number is positive and that number is odd, you got to be careful. Well, the problem we have, oh boy, hold on. Is exactly that. Hold just a second. In other words, when I was trying to determine what is that when x is to the left of 1. Well, when x is to the left of 1, we're going to have a negative number to a fractional exponent.
Yeah.
So I don't know if that's greater than 0 or not. When x is to the right of 1, it's clearly positive.
Yeah.
Now, this is kind of something I've struggled with for 8 years. Most of the Denver school system does not recognize this principle that if you can't take a negative number to a fractional exponent. But if you could, well, the cube root of a negative number is negative and squared is positive, so it would appear to be positive to the left of 1. So this function looks like it might be increasing across its entire domain. Although I would be reluctant to say that because of that, what we just talked about. But I don't want to get into that now. I don't want to argue about this principle. It doesn't really have much to do with calculus. The fact of the matter is if the original function is increasing, the first derivative is positive. If the original function is decreasing, the first derivative is negative. Let's see, what else do they ask? This is number 30, right?
Yeah. So they ask for the
first derivative test to identify all relative extrema. Well, it looks like we probably have a relative extrema at 1. But for it to actually be a relative extrema, remember the derivatives have to change signs on either side of that point.
Right.
Well, again, it's tough to tell.
Yeah.
I'm going to input this into Wolfram Alpha just to see what this function looks like, just so I can eliminate this problem. X minus 1 to the 1/3. One day I'm going to find the answer to this problem.
Yeah. And make millions.
Well, it's really an interesting mathematical dilemma. So this was our function. and they graph it. Now, the blue graph is the real part. The red graph is the imaginary part. And they're giving us two different zoom levels. Well, if we look at the real function, we knew we had a critical point at 1.
Yeah.
Well, what do the slopes do going into that? Are they negative or positive?
Negative.
What are they coming out of it?
Positive.
That means that should be a minimum. In other words, at 1, we have a minimum, and the graph verifies that we have a minimum. Okay? So we can use the first derivative test to verify that this is a minimum, because the slopes go from negative to positive. You can forget, I guess, everything I said about negative numbers to fractional exponents, because this does not appear to affect that. In other words, this definitely gives you a negative. Now, I am a little curious about what the second derivative is. Let's just apply the second derivative test. In other words, let's forget this. Clearly, when I graphed this, these were all negative, not positive.
Yeah.
So when x is a negative or less than 1, this is a negative number. Somehow. I'm not sure how. Because when you take the cube root of a negative number, you get a negative number, and when you square it, you get a positive number. So to my way of thinking, this should always be positive, but it doesn't look like it when I graph the original function. The original function clearly goes negative slopes to the point 1 and then positive slopes. So it is decreasing whenever x is less than 1. It's increasing whenever x is greater than 1. And that kind of follows that line chart. You can see that the slopes go from negative, negative, negative to positive, positive, positive. So, let me look at the question again. Oh, where'd it go? Wow. Where did it go? Oh, it's in my book. Sorry. Apply the first derivative test. We did that. And then use a graphing utility to confirm your results. And we did that. In other words, we used a graphing utility to see that this is what the function looks like. And always make sure, Brianna, that you're distinguishing between the function, the first derivative, and the second derivative. What we are looking at here is the function. That's the function, x minus 1 to the 1/3 power. And if you look at it, you can see that there is a local minimum at x equal 1. And that the derivative is not actually defined there. Right? In other words, I can see that I'm looking at a cusp or a corner. Furthermore, if I actually look at the derivative, well, I can see that it's not defined for x equal 1. I'd be dividing by 0. So our graph certainly matches what we have discovered about this function, is that it's not defined at x equal 1, and that it's still a local minimum because the first derivative test shows me the slopes are negative, 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 undefined, positive, 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 positive. So the slopes change direction going in and out of the critical point that is not defined. That's all you need. We have completed the problem. What next?
Question 36.
Okay. Whoops. I was wondering whether he was going to give you 31 and 32 or not, because those are definitely different. What's going to be the first step here?
Move the x squared into the numerator.
Well, the first step's going to be take the first derivative, right? That's always the first step. But there's numerous ways to take the first derivative here. I could use the quotient rule, right? I'm looking at a quotient, but the quotient rule is hard. Quotient rule involves not only a lot of complex algebra, but a lot of complex simplification. So if you do not have to use the quotient rule, let's not use it. Well, this thing is also equal to this. See why? So all I'm doing is splitting it up into two fractions. That fraction and that fraction. And the advantage of doing that is I don't have to use the quotient rule. In other words, now I've got a function that says x to the minus 1 plus 3x to the minus 2. Well, that's f of x. What's f prime of x? Much easier to do it this way than to use the quotient rule.
Yeah. So it's negative x to the negative second power minus 6 x to the negative third.
And it's a good idea to write these as positive exponents, because that immediately tells us x cannot be 0. And this also tells us x cannot be 0. And so we know instantly that a critical point is 0.
Right.
But are there any other critical points? In other words, are there any slopes of the tangent line that are equal to 0? Well, let's do the algebra on this. This is equal to x over x cubed negative minus 6 over x cubed. That's equal to minus x minus 6 over x cubed. Well, where is that equal to 0?
At negative 6.
Yes. In other words, the only thing that makes a fraction equal to 0 is if its numerator is equal to 0. So I set that equal to 0, and what I get is x equals negative 6. So that's another critical point. In other words, remember what I'm looking for. I'm looking for all points where the first derivative is undefined or equal to 0. Well, it's undefined at x equals 0, but it's equal to 0 at x equals minus 6. If you plug in minus 6 here, you see that this is equal to 0. So I've got two critical points. Let's plot both of them, and let's figure out whether the function is positive or negative on either side. What is it to the left of minus 6?
It was
We have to go in not to the derivative function, but to the original function.
Oh.
In other words, what is the original function when x is a number less than minus 6?
Okay.
Oh, hold on. My mistake. We go into the derivative function. Because what we're graphing here is the first derivatives, whether they're positive or negative. Remember, we're going to end up using a first derivative test. So we need to know what the first derivatives are going into these critical points. So if you plug in a number to the left of minus 6, what is this function? Positive or negative? Sorry, what is this function? Positive or negative? First of all, pick a number to the left of minus 6.
Minus 7.
Okay, good. Means our derivative is minus 1 over 49 minus 6 over minus 243, which is 7 cubed. Is that a positive or a negative number?
Negative.
Well, we got minus 7 plus 6. So you're right, it is negative. So if I go to my line chart, everything over here is negative. Now pick a number between 0 and minus 6.
1. I mean negative 1.
Negative 1. Now let's figure out what the first derivative is of negative 1. Is it greater than or equal to 0 or less than 0? Well, negative 1, what do I get? What is f of negative 1?
Negative 1 over negative 1 squared.
Which is negative 1.
Minus 6 over negative 1 cubed.
Which is minus a negative 6. Right? I do that right? In other words, negative 1 cubed is negative 1, so that becomes negative 6, so it's minus a negative 6. So that's actually positive. So to the right of negative 6, it's positive. And now to the right of 0, pick a number.
1.
Okay. What is f prime of 1?
Negative 1 minus 6. Negative.
Which is a negative number.
Yeah.
So it becomes negative. These usually alternate when you have these line charts. However, they don't always alternate. I had a student tell me once that their teacher told them they always alternate. So once you figure out the first one, you're done. But then I came across a function where they do not alternate. So it is not true that they always alternate. However, what you can see is that the derivatives go from negative to positive at negative 6. What does that make negative 6? Maximum, a minimum, or neither?
A minimum.
Yes. How about at this point here where they go from positive to negative?
Maximum.
All right. So the only thing we need to do is to plot the function and prove that we're correct.
Mm-hmm.
X plus 3 over x squared. And it's really important to distinguish between whether you're talking the function, the first derivative, the second derivative. It's very confusing a lot of times as to which you're supposed to use. Okay, well there's my function. Okay. Now, I can tell that first of all it's not differentiable at x equals 0.
Yeah.
I've got an infinite discontinuity. And whenever you have discontinuities at all, it's not differentiable at that point.
Mm-hmm.
However, ooh, this is very tricky. I do find a point at -6. Can you see that?
Yeah.
That actually appears to be a minimum. You don't see it on the zoomed in graph above, but you do kind of see it on the bottom graph.
Right.
And that's what we figured out, was that I have a minimum at -6. That's what this said, was that I have a minimum at -6. I have a maximum at 0. Ooh. Turns out that I don't really have a maximum at 0.
No.
You know why? Because infinity is not a maximum.
Ah.
In other words, what I have at 0 is I go to infinity on the left and I go to infinity on the right. But that's not, and my slopes go from plus to minus. So even by the first derivative test, it appears to be a maximum.
Mm-hmm.
Well, let's take a look at the second derivative test. Let's see what the second derivative is. This is the first derivative, right there, f prime of x. Let's erase everything else and figure out the second. In other words, perhaps the second derivative can resolve this problem that we have.
Mm-hmm.
Well, let's see. That's x to the -2, so it becomes plus 1 over x cubed. This becomes 6x to the -3, so it becomes plus 18 over x to the 4. So that's f double prime. And notice that f double prime is also not defined at x equals 0. It's neither positive nor negative. And if we're looking for concave down, we're looking for a negative number. If we're looking for concave up, we're looking for a positive number. Well, this is neither. It's not defined, which fits this picture perfectly. The first derivative would not be defined at x equals 0. It's not differentiable at x equals 0. So the second derivative isn't going to be defined there either. And that's maybe something important to learn. If the first derivative is not defined, the second derivative is also not going to be defined at that x value. So I cannot apply the second derivative test because the second derivative test is not defined. And when the second derivative test is not defined, it means it's not either a maximum or a minimum, despite the first derivative test. The first derivative test would indicate that it's a maximum because the slopes go from positive to negative. And that usually indicates a maximum. In other words, we would have concavity down. But if you had concavity down, then the second derivative would be negative. And our second derivative is not negative. It's undefined. So we don't have concavity down. Sorry to make this so complex, but I didn't pick the problem.
Yeah.
Your teacher did. I would actually prefer to work on problems where we don't have these questions of not being defined at a point. It, I believe, makes the problem a little more understandable. In other words, that was a very difficult problem because it passed the first derivative test indicating it was a maximum, but it didn't really pass the second derivative test.
Right.
Usually it's the other way around. In other words, if you do the second derivative test and you come up with 0, then it says that you can't use the second derivative test. You got to go back to the first derivative test. Okay? But if you use the second derivative test and you don't get 0, but you get undefined, that means that it's neither a maximum nor a minimum, and the first derivative test is not going to help you. Because the first derivative test indicated it was a maximum. And yet we can see from the graph that even though one might think that that would be a maximum at x equals 0 because y goes to infinity, it really isn't. For something to be a maximum, you have to be able to put a number on it. And infinity is not a number.
Right.
So the fact that it goes to infinity on either side of 0 does not make it a maximum at x equals 0. All right. That might be one of the more complex things I've ever tried to explain to anybody. Well, it is, because you got three things going on. You got a second derivative test, you got a first derivative test, and then you got a function that's not differentiable at a point. And if it's not differentiable, then there is no first derivative at x equals 0. And if there's no first derivative, there's no second derivative.
Right.
All right. That was 30. What next? No, that was 36. Sorry.
About 39.
Sorry. I just looked at my clock and I realized we're 3 minutes over.
Oh, yeah, I didn't notice.
I happen to have an appointment at 3:30 that I am 3 minutes late for. So
Sorry.
That's okay. I don't set alarms usually. I leave it up to my brain to read the time, but I missed it this time. So I'm going to let you go, Brianna, and I will talk to you the next time.
Thank you for the help.
You're welcome.